Okay, let's review a little bit. What do we use to represent a vector?
An arrow.
An arrow, good. And we draw it in what direction?
Whichever way it's going.
That's right. We draw it in the direction of the motion, right? We draw it in the direction of the motion. We need to try to draw them to scale. And how do we draw our vectors if we have multiple vectors? Do we draw them all from the origin? No, we draw them tail to tip, or one right after the other. Good. Does it matter the order in which we draw our vectors? It actually doesn't. We haven't talked about this, but it actually doesn't. We can add them in whatever order we want. So let me demonstrate this a little bit before we start drawing and talking about our resultant vector. Let's say that I went east, then south, then east again, then north, and I stopped. Okay, let's say I did all of these things. So I'll put some numbers on these. 4, 6, 3, 2, right? That's my path. Okay, or I had 4 vectors I needed to add together. My final resultant vector is the graphical sum of all these vectors put together. And so it goes from the origin to the tip of our last vector. That red line is basically like a bird's eye view of where I'm going versus where I started, right? So that is called the resultant vector. Does that kind of make sense? The resultant vector always resets and starts from the origin to the tip of the last vector. Now, let me demonstrate here. It does not make a difference the order in which we add our vectors. Let's say, I'll go backwards this time. I'll go north 2, east 3, south 6, and east 4. Okay, I didn't draw them exactly to scale, but look at my resultant. Does it look very similar? They should look identical, right? Because it's giving me the same final location. So the order in which we add our vectors makes no difference. It will always put us in the same final location. That does look pretty identical. I'll take credit for that one, okay? So it doesn't always turn out that way. Okay, my day's looking up from that based on this drawing, okay? But the order in which we add our vectors does not matter. It is important, though, that they lead us somewhere. It takes us somewhere from the origin. Okay, does that kind of make sense? Resultant vector is the graphical sum. It's the overall vector. Any thoughts on how can we calculate my final displacement here? Is there a way I can find how long that line is? Any thoughts? We're gonna know in a couple minutes, but any thoughts right off the bat? How could I figure out how long that red line is? Okay, yep. So Maddie's on the right track. We're going to eventually just find the sides and find the hypotenuse of that triangle, right? We're going to be able to find out how long is this side of my triangle, how long is this side. Or inversely, I can find, this side, right? I need to make that resultant vector the hypotenuse of a right triangle, and then I can be able to find its side. So we're going to be able to solve for vectors graphically. That's us drawing them, and we're going to solve vectors algebraically, which means we're just going to do the math with them, right? We'll be able to look at it both ways. So let's go ahead and start looking at a resultant vector example. This example is just a runner that is moving forwards and backwards. That's it. So they're stopping and starting, turning around, moving back, whatever they're doing. But we're going to start at the origin. Our person's going to run forward 2 meters, then backward 6 meters. Do I go back to my origin and start going back 6? I go right from where I ended. So I'm going to start here and go back 6, then forward 4, and then forward 5. So I drew all of those vectors tail to tip. My resultant vector then will be from the origin to the tip of the last vector. Agreed? You see that pink line? It's kind of hard to see the difference there. Do you see my pink line? My resultant vector is plus 5 meters, or you could say forward 5 meters, or however you want to say it, right? When we have motion that's simply back and forth, finding the resultant is really easy, right? It's just an object that's moving in the same direction. Okay. Let's look now at objects that don't necessarily move in the same back and forth pattern, okay? This says I move 11 kilometers north and 11 kilometers east. I actually want to flip-flop this for a second. Instead of 11, I want to make this 9 kilometers east. Okay, I'll tell you about why here in just a little. I don't want a 45-degree triangle, but so that's why I'm changing this. But I want to make this 11 and then 9. So I'm going to draw my system, and I'm going to count each of those blocks as 2 kilometers. So I'm going to go 2, 4, 6, 8, 10, 11. So like a half right there. There's 11. And then 9. 2, 4, 6, 8, 9 kilometers. So this side is 11 and this side is 9. Okay, so I want to find the resultant vector of this problem. So we're going to take our resultant vector and we're going to add it from the origin to the tip of the final vector. Okay, these are displacement vectors, which means they must have what two things? Magnitude and direction. They have to have magnitude and direction. So let's be thinking about that while we're working through this. I need to know what's the length of that blue line. What's the length of that blue line? How can I find that? What's it called? Pythagorean theorem. I'm going to use Pythagorean theorem to find the hypotenuse of this triangle. We're almost always going to deal, I'm not even going to say almost, we're always going to deal exclusively in right triangles. We're going to boil everything down until we get a right triangle. Okay? And so we're always going to be able to solve with Pythagorean theorem and then sine, cosine, tangent. So do you remember Pythagorean theorem?
A squared plus b squared.
Good. A squared plus b squared equals c squared. We're looking for c right here. C is the hypotenuse. So to find my question mark side, I would take the square root of 11 squared plus 9 squared, right? In my calculator, I can do it in one swoop, right? I plug in second square root of 11 squared plus 9 squared, and I should get a number greater than 11, agreed? Okay, so let's try that. I get a value of 14.21 kilometers, but I started with whole numbers, so I'm actually going to round that down to just 14 kilometers. Okay? 14 kilometers. Any questions about the Pythagorean theorem part? That should be something we feel pretty comfortable with. We're good? Okay, and so this is the magnitude of my vector, but now I need the direction. So if this is my origin, this is my starting point, what direction did I have to leave to get to my end point? Northeast. But is northeast specific enough direction? Because northeast could mean I walk this way. And northeast could mean I walk this way. And northeast could mean I walk this way. It could mean anywhere between 0 and 90 degrees. It is not specific enough. So we have to not only give the magnitude, but the direction includes the angle at which we need to leave the origin. Okay, so that means we're going to zoom in on our triangle right here, and we're going to find this angle that touches the origin and figure out I need to leave 30 degrees northeast, right? We're going to give a little more detail here in a second, but I have to find the angle that goes with it. So let's think about trig functions here to solve for our angle. Any thoughts? We have the opposite side and the adjacent side, right? This is opposite, adjacent, and hypotenuse. We technically have all three. Here's my thought process when I solve these problems. If I try to use the hypotenuse to solve for my angle, and I accidentally solve the hypotenuse wrong, now my angle is wrong also, right? I like to use the numbers I've been given to help solve for my angle. So here's the way I solve for it. If I have the opposite and adjacent, that leads me to using tangent. Agreed? Tangent of theta, some angle, is equal to the opposite side over the adjacent side. I have to do something special with my calculator when I'm solving for the angle. Do you remember what that is? Because we don't know theta. Theta is our question mark. I don't just press tangent, I have to press reverse or inverse or second tangent. So I'm going to press second tangent, and that'll open up a parenthesis with me, but it'll look like this. tangent -1, and I'm going to enter the opposite side divided by the adjacent side. So second tangent of opposite over adjacent, and I get 39.3 degrees. If you're not, I want everyone to go ahead and plug that in their calculator so we know that we're working with degrees, not radians. Our calculator needs to be in degrees. So if you're not getting 39.28 or 39.3, make sure we can get that fixed. Because in here, we always want our calculator to be in degrees. Okay, did it come out okay? When we're solving for the side, we use Pythagorean theorem. When we're solving for the angle, we have to use second tangent. Okay, and again, I almost always will follow that pattern, second tangent. Could I use second sine? Yes. Could I use second cosine? Yes. But I don't want to use the hypotenuse in case I messed up when I was solving that. Okay, so now we're getting close to a final answer, but we're really not even there yet. Our final answer would be written something like this. Let me still keep our triangle. It would be 14 kilometers at an angle of 39.3 degrees. And here's my other question. Can I just say northeast? Because 39 degrees could mean northeast here, or it could mean 39 degrees northeast here, right? It's 39 degrees up or 39 degrees over. We don't know until we give ourselves a label. So what we do is we find this angle right here, and we determine, we can't just say northeast, we have to just say, is it north of east or is it east of north? Okay, look at your angle, look at the triangle we built, and determine, is this angle right here, is it east of north or is it north of east? It is east of north. East of north. So let's figure out why. East of north. The way I do it, I'm looking at my angle here. Do we see the right angle that's formed? Okay, I want the whole angle. I'm just looking at this guy right here. That's our 39.3 degree angle. I determine what axes is it touching. Tell me what axes it's touching. So northeast, southwest, which one is it touching? It's touching the north axis. And so then I decide, is my triangle, it's touching north. So does my triangle swing east of north or does it swing west of north? Those are my only two options. It can't swing south of north. So if it's touching the north, is it going east of north or west of north? What do we think? East of north. So that's how we come up with that. The other way you can do it is to just write them backwards. Okay, in our example, we went north, then east, and so my angle becomes east of north. You could just do it that too, right? It goes backwards. My triangle is east of north, right? Make it backwards of how you wrote your actual triangle. Okay, how do we feel about that? Let's try another one. I think I don't have a slide for another one, but I want to actually do another one here. So I'll erase this one. You can just do this on some extra practice, extra whatever you have there. No problem. Okay, let's say that I went 6 meters west and then 7 meters south. 6 meters west, 7 meters south. So here's the way I draw this. I always start my diagrams with a little origin like that. So it tells me where is my starting point. Because sometimes what people will do is they'll draw a triangle and then you don't know, well, like, where did we start from? Is it this angle I'm trying to find or this angle I'm trying to find? It's hard to tell without the origin there. So I always start with a little origin. Okay? And does it matter if I go south first or west first? It doesn't matter. So I'm just going to go in the order they gave me. So 6 west and then 7 south. And I'm going to draw my resultant vector. Okay, my goal is to find my final displacement. So I want my hypotenuse and I want the angle, because that's what I would need for the entire vector. Okay, so to find my hypotenuse, or to find the magnitude of my displacement, I'm going to use Pythagorean's theorem. So square root of 7 squared plus 6 squared gives me 9.22. Okay, and if I wanted to round it to a whole number, I could. Again, I'm really not picky about that kind of stuff. Okay, I really like to have 2 decimals. That just feels comfortable for me, so that's where I like things. But the rounding on it is not that big of a deal. 9.22 meters at, and now I have to find the angle that goes with it. So in my calculator, I would do second tangent of the opposite side, which is 7, over the adjacent side, which is 6. So second tangent of 7 divided by 6. And that gives me 49.4. So this is at 49.4 degrees. Okay, and so here's my origin. Can we just say southwest? Nope, that won't work like that. What do we think? Is it south of west or west of south? South of west.
What?
It's south.
I thought you said it was supposed to be opposite of what you drew.
We went, it's the opposite of the order you go in. So we went west first, then south. So my things get listed south first, then west. Okay. Or again, I like to just look and see, it's touching the west axis. It's touching the west axis right here. My angle is touching the west axis. And then I decide, does my triangle swing north of west? No. Does it swing south of west? Yes. All right, that's my preferred method of that, understanding that. But that's really up to you. Okay? Now let me ask you one other question. What if you had reported to me that the angle was 40.6 degrees west of south? Do those two angles the same? I'm sorry, that's not a very good question. Do these angles lead me to the same final destination? These angles are complementary, aren't they? Don't they add up to 90 degrees? Okay, so here's the thing. If I were to have drawn my vector south first and then west, I would have been solving for this angle, which would have been west of south. And this would have been 6, and this would have been, all right, I would have gotten the complementary angle. So you will never need to report both, but they are both correct. So if you do it one way and your friend does it another way, as long as you both have complementary angles to one another, they add up to 90, then they're both correct, right? As long as you have them labeled, right? Yeah, if I want to draw this vector here, I'm going to start with my origin, right? I always draw the little crosshairs to get me started. East of south means I'm going to be going somewhere in this quadrant right here, agreed? It's going to be somewhere southeast. So I'm not super worried about the drawing it to exact scale. So I just kind of draw my vector somewhere arbitrary in that direction. Okay? I'm not trying to necessarily draw it all the way to scale, but I know it's got to go somewhere in that direction. So then I decide I want my vector to be east of south. So which axes do I need to be touching? I want to go east of south. So I need to touch the south axis and make my triangle swing east of that. So my angle would go right here, 16 degrees. Okay. Or again, if you want to walk it backwards, if my angle is east of south, that means that I went south first, then east, and then I closed my triangle, right? And that's the angle I formed. We doing okay? Okay. We're going to do a lot more work with vectors at angles a little bit later, but I wanted to at least introduce you to vectors in this way, right? The simple vector addition. Yeah. All right, let's move into velocity. And for some reason, my slide printed crazy, so yours looks a little different than mine, I assume. Yes? Does yours print better than mine? Okay. When we're talking about velocity, here's our first main equation, okay? Velocity is equal to change in displacement over change in time. Do you recognize this little triangle symbol right here? It's a Greek letter, and what's it called? Delta. Good, and it means change in. Or more specifically, it means final minus initial. So whenever we see that delta, we're going to take the final something minus the initial of whatever that thing is. And do you remember, what does X stand for? Do you remember? X is our displacement, right? And that's how far we've gone. What's the unit that we use for displacement? If we're talking about length covered, it would be meters, okay? And then in terms of our time change, very rarely do we actually have to do a subtraction for time. Usually they just tell us it took 4.2 seconds for it to happen, right? That is the change in time. So we're not having to do math for that part. So I almost really hardly ever write that delta for t, okay? When we really write our equation for velocity, usually you'll just see me write displacement over time, right? Because I know that I have to find it, or I might write delta x over t or something, but with t, we don't have to do that subtraction very often. We said that this is measured in meters. What would time be measured in? Seconds. So that makes the unit for velocity meters per second. Meters per second. So that's when we did all those conversions. We really worked to convert to meters per second because we're going to use it really often. So since velocity is a vector and it has to have direction and magnitude, what would it mean if we say that our velocity is equal to negative 10 meters per second? What do you think the negative tells us? Going downward or going backwards? Good. The negative here indicates direction for us because I can't go so slow. I'm going slower than 0, right? I can't go slower than 0 meters per second, right? Agreed? We can't go negative meters per second. That doesn't happen, right? So the negative has to just tell us the direction. So it could mean south, it could mean west, either way. Okay, but that's what that negative tells us. So this could direction could be either plus, minus, or it could be north, east, south, west. Okay, could be our cardinal directions. Here's the rule that I like to give you. If you're given a cardinal direction in the problem, you know what cardinal directions are? North, east, south, west. Okay, good. If you're given those in the problem, then you need to include it in your answer. If you're not given a cardinal direction, then plus, minus is sufficient. Okay? All right, very good. Let's try this problem here, okay? Based on the equation we just learned, velocity equals displacement over time, right? That's what we're thinking through here is this velocity equals displacement over time. A car travels with a velocity of 50 meters per second east for 2 minutes. 50 meters per second east for 2 minutes. They then turn south and travel 30 meters per second for 2 minutes. What was the total distance covered and what was the displacement? So we're asked for two different things here. Can you remind me of the difference between distance and displacement? The difference between distance and displacement, what is it, Kayfa? How much what?
I don't like how removed it is.
Yeah, good. Distance is total meters traveled. Back, forth, start, stop, whatever it is, total. Displacement is how far we are from where we started. So this is going to be a problem we do in several parts. In our physics problems, we can't take all of this complex information and plug it into one equation, right? If our motion is made up of different parts, then we need to solve our problem in those parts, okay? We can't lump everything together. We have to compartmentalize based on motion differences. So we're going to solve the first segment, which I'll have it underlined in purple, when he's traveling east, okay? It says 50 meters per second for 2 minutes. Do you see any red flags there? They don't match, do they? So we need our time to match the time unit of our velocity. So that means we need to convert that to seconds. So we're given our velocity is 50. We're given our time at 2 minutes. So how many seconds is that? 120 seconds, and we don't know our displacement or the number of meters we went during this segment. So we're going to plug that into the velocity equation and solve it. So 50 is equal to x over 120 seconds. Okay, so how could I get x by itself in the numerator here? How can I solve for x? Yeah, I'm just going to multiply by 120 on both sides. Okay, so by 120, and I get 50 times 120 to equal 6,000 meters. And what direction was that 6,000 meters happening? This one was east. Okay, so they traveled 6,000 meters east during the first segment of the motion. Are we all on the same page for that one? We comfortable with the equation and how it got plugged in? Okay, let's move to part 2. Says they turn south and travel 30 meters per second for 2 minutes. So we're going to use the same equation. 30 meters per second equals displacement over 2 minutes, which we're going to put into seconds. Right? Are those conversions one we can do quickly and plug in? Okay, very good. So same thing. 120 times 30 gives us 3,600 meters. And what was the direction for this one? South. Okay. So my question first asked me for the distance traveled. How can I find the total distance I traveled? All I'm going to do is add them together. Right? I'm going to add them together. And I know that I went 6,000 east and 3,600 south. And so my final is 9,600 meters. And do I put a direction on distance? I don't, because I can't. I didn't travel a single direction for all 9,600 of those meters, right? So I can't include a direction there. Okay, but now it asks me for my displacement. So how can I find displacement? I'm going to use my Pythagorean theorem or my vector addition. So I'm going to go east, 6,000, and then I'm going to go south, 3,600. And now I can find my displacement. Okay, and so I'm going to have to include both the magnitude and the direction, okay, or the hypotenuse and the angle. Okay, so Pythagorean theorem there to find the side. And since all of the rest of my numbers are pretty nice and round and whole, what could we round that hypotenuse to? All right, we can round that to about 7,000 meters. Okay, I got 6,997. So we can go ahead and take that to about 7,000 meters. And then I'm going to find my angle. So I'll take second tangent of the opposite side, 3,600 divided by the adjacent side. And I get an angle of about 31 degrees. Is everyone's angle coming out okay? Your calculator's in degrees, not radians? Okay. Is my answer complete? What am I missing? The direction. Okay, so now I'm going to look at my triangle, right? Here's my origin. And for me, I'm going to look at it and say it's touching the east axis. And so then I think it's going south of east. Right? East. So it's 31 degrees south of the east axis. That's where I'm going to go. Okay. And there is my final displacement. We need to drive 40 kilometers east in 32 minutes. So what's my velocity in meters per second? And then what will it be in kilometers per hour? So I want the answer in 2 different units. They represent the same velocity, but the units will be different. So I'll give you a couple minute head start and then we'll see where we're at. The last thing we're going to look at here is the difference between speed and velocity. We almost exclusively use velocity. Once we're done differentiating the differences between the two, we will almost exclusively use velocity. Okay? Now, the terms speed and velocity often get used incorrectly, interchangeably, just like mass and weight. Okay, but they get used incorrectly. But speed is the scalar quantity of velocity. It is distance divided by time. And we know the difference between distance and displacement. So it is distance divided by time. It has no direction because it is scalar. Scalar means it is a measurement that only has a magnitude. Okay, so just like distance, we don't put a direction on it. We won't put a direction on speed either. Speed cannot be negative because negative only indicates direction. Remember, in terms of velocity, negative only indicates direction. I can't go slower than 0. Okay, so we can't have a negative speed. Velocity could be negative if we so needed it to be. Okay, so let's try this one here. It says, what is the average speed? We already worked through this whole problem. And we found distance and displacement, right? This problem look familiar? We already found its distance. So if I want its speed, I would take distance divided by time. What did we say the total distance traveled was? Can you look back on that problem and find out what was my total distance traveled? 9,600 meters. And how long did it take for me to travel all of those meters? "240 seconds, right? Because that's 4 minutes. So that means I traveled an average of 40 meters per second, right? Which that makes sense because we went 50 for half the time and 30 for half the time, right? So it makes sense. Do I include a direction with that? No. This is what we often calculate when we take road trips, right? Did we really travel 60 miles an hour the whole way? No. We were 55 for part of it. We were 70 for part of it. We were 45 going through town. We were whatever, right? But it took me 3 hours to travel, I don't know, 180 miles, right? So I traveled on average 60 miles an hour. That's the same type of calculation that we're doing here. The average velocity, though, is different because we're taking the displacement divided by the time. Okay, and so displacement in our case, I think, was 7,000 meters divided by 240 seconds. And so I'm going to get a little bit of a faster value there. 29, sorry, a little slower, I apologize. 29.2 meter per second. And this one would be at whatever that angle was that we had last time, 31 degrees east of south. Right? Because I don't have to travel the full legs of the triangle, I can go a little slower on my way there. All right? That would be what I'm looking at. Okay, any questions? Very good.